Hello students, welcome to WebStudyz. I am Abhishek and today we will be covering equation of continuity, which is a very important topic in fluid dynamics. So equation of continuity, it basically represents that the product of cross-sectional area of pipe and the fluid speed at which any point along the pipe is always constant. Fine. This product is equal to the volume flow per second, or simply we can say that the flow rate. Fine. Equation of continuity, it can be given as R equal to AV, which is equal to constant. Here R is the volume flow rate and A is the flow area, or we can say the cross sectional area, and V here is the flow velocity. Fine. So now what is the importance of this continuity equation? So it provides us very useful information about the flow of liquid as well as their behavior during their flow in a pipe or a hose. Talking about the applications, so it is used in a variety of objects including tubes, pipes, rivers and ducts that carry gases or fluids. Fine. So according to equation of continuity, we have some assumptions. The first assumption is the tube is having single entry and single exit and no entry exit in between. Fine. Then the fluid flowing in the tube is non-viscous. Next one is the flow will be incompressible. Also the fluid flow is steady. So these are the assumptions which we need to make before solving the problem of equation of continuity or applying this. Fine. Now let us derive this equation of continuity. So we will be observing this figure which is made on the upper right side of the screen. Fine. So now we have to consider the fluid flow for a short interval of time in the tube. So we will assume that short interval of time as time del t. Fine. In this time, the fluid will cover a distance of x1 with a velocity v1 at the lower end of the pipe. So at this time, the distance covered by fluid will be, we can write distance covered by fluid will be del x1. So del x1 will be equal to v1, which is velocity of flow into time, since we know that distance is equal to velocity into time. Fine. Now at the lower end of the pipe, the volume of fluid which flow into the pipe will be v, volume v, and this volume v will be equal to a1, that is cross sectional area, into del x1. Fine. So this del x1 can be written as v1 into del t, which we will substitute here. Fine. So it is known that the mass is equal to density into volume. So mass of the fluid in del x1 we can write. So we will have del m1 for small mass. This will be equal to density into volume. So density we can have as rho 1, and volume we have calculated above. So it is a1 into v1 into del t. Fine. Now similarly, now the mass flux has to be calculated at the lower end. Mass flux is simply defined as the number of mass of the fluid per unit time passing through any cross sectional area. So for the lower end with cross sectional area A1, mass flux we can write as del M by del t, del m by del t. Basically t we have shifted to the left hand of the equation. So this will be equal to rho 1 into a1 into velocity v1. Fine. So we can name this as equation 1 for now. This is our equation 1. Similarly, we can write for the upper end of the tube. This upper end. Fine. So if we write for the upper end of the tube, similarly we will get here as this will be m1, and here we will have m2 equal to m2 by t. For the time here is constant since same time we are using. So this will be equal to rho 2 into a2 into velocity v2. Fine. And this will be our equation 2. Fine. So here v2 is the velocity of fluid at the upper end through x1 in time t, x2 in time t, and a2 is the cross sectional of the upper end. So in this, the density of the fluid between the lower end of the pipe and the upper end of the pipe remains the same with time on as the flow is steady. So the mass flux at the lower end of the pipe is equal to the mass flux at the upper end of the pipe. So therefore, these both equations are equal. So we can write rho 1 a1 v1 is equal to a2 v2, and let me name is as at equation 3. Fine. So this is our equation 3, and now this can be written in general form as we can write rho into a into v is equal to constant. Fine. So the equation proves the law of conservation of mass in fluid dynamics. Also, if the fluid is incompressible, as we have read in the assumption, then density will remain constant for steady flow. So here our density rho 1 is equal to density rho 2. Fine. So if this is equal, then from here we can write one more equation, that is a1 v1 is equal to a2 v2. Fine. And in general form we can write this also as a into v is equal to constant. Fine. So now R is the volume of rate of the flow. So this above equation we can represent this as R equal to AV, which is equal to constant. So this expression R equal to AV, which is equals to constant, it is our equation of continuity basically. Fine. Now let us solve a problem. The question is, water flows through a pipe of internal diameter 20 centimeter at the speed of 1 meter per second. Then what should be the diameter of the nozzle? B if the water is to emerge at the speed of 4 meter per second. Fine. So according to equation of continuity, rate of the flow into the system is equal to rate of flow out of the system. So firstly here we are given diameter D1 as 20 centimeter. Fine. And From here we can write radius r1 20 by 2 is equal to 10 centimeter, which can be written as 0.1 meter. Fine. And velocity v1, it is given as 1 meter per second. Velocity v2, it is given 4 meter per second, but we need to find the diameter d2, and therefore radius we can find r2. Fine. So according to equation of continuity, we can write a1 into v1 is equal to a2 into v2. V is the velocity, but we need to find the area. So this pipe will be circular, means it is basically cylindrical, so its cross sectional area will be circular. So cross sectional area is basically pi r square. So pi into r1 square, 0.1 square into v1, this will be equal to pi into r2 square into 4. This pi and pi will get cancelled out. We will get r2 equal to 0.1 square into 1 divided by 4, and this whole part be under root. This will be equal to 0.05 meter, or if we convert this to centimeter, we are going to get 5 centimeter, which is our correct answer. Let us solve one more question. Here it is asked that an ideal fluid, it flows through a pipe of circular cross section made of two sections with diameter 2.5 and 3.75 centimeter. We need to have the ratio of velocities of both pipes. Fine. So the first diameter we have is d1, which is 2.5 centimeter. Second we have is d2, which is 3.5 centimeter. From here we can calculate the cross sectional areas also. So cross sectional areas will be basically, if we have diameter, then we do pi by 4 d square, and in case of radius we do pi r square. Fine. So using the equation of continuity, we can write a1 into v1 is equal to a2 into v2. Fine. So if we do v1 by v2, this will be equal to a2 by a1. Fine. Let us put the values. So pi by 4 by pi by 4 into d2 square, that is 3.75 square by pi by 4 into 2.5 square. This will be equal to 9 by 4 if we calculate the values. Fine. So this is our answer. So I hope you have understood this topic, and thank you.